Swayam Prabha. Digital India. Educated India.
So, good afternoon everyone, and today we will continue with the module number 5, that is principle of texture measurements by X-ray diffraction. So, this is lecture number 23, in which we will try to understand the penetration depth of X-rays, neutrons and electrons in a more fundamental level, and then we will go to basics of X-ray generation. The concepts that will be covered is X-ray, neutron and electron diffraction and its mass absorption coefficient leading to its penetration depth, and how continuous X-rays are produced and how the characteristic X-rays are produced. So, X-ray diffraction method. X-rays are basically electromagnetic radiations which are scattered by shell electrons of the atoms which are present in a periodic arrangement inside a polycrystalline metal or alloy. So, here the interaction is between the X-ray, which is electromagnetic radiation, and the charged electron, leading to scattering and thereby diffraction. Now, this interaction produces diffracted X-rays. However, the incident beam of these X-rays are basically divergent and its wavelength is also smaller than the periodic lattice arrangement, but it is quite high, and therefore it has a spatial resolution of 100 micrometer and an angular accuracy of 2 degrees. So, as we said that it measures average texture from the surface up to few micrometer depth penetration and gives macro texture. So, synchrotron X-ray method are specialized radiations which are obtained in a beamline where there is a synchrotron accelerator, and it can produce short wavelength lower than the natural X-rays. The wavelength is that it can produce are shorter than the wavelength of natural X-rays, and thereby they can be made parallel. They have minimum angular divergence and therefore can be made into small beam, thin beam size. It has very high intensity because of its lower wavelength. You know that the energy of the radiation is inversely proportional to the wavelength, and therefore lower the wavelength, the energy of the wave is much higher. So, it has higher penetration depth and therefore it can obtain macro texture. Because of very thin beam size, it can have very high spatial resolution. So, because of high resolution 0.1 to 100 micrometer, one can adjust higher angular accuracy of 0.1 degrees. It can give micro texture as well. So, if we look into these X-ray diffraction methods, the absorption of these X-rays, means the normal X-rays and the synchrotron X-rays. Let us talk about the normal X-rays. Depends upon the value mu, which is given here. This mu is basically the linear absorption coefficient. Usually mu is not used, but mu by rho is used, where rho is the density, that is the specific weight of that material in which the X-ray radiation is basically interacting, right. So, mu by rho, which is in unit centimeter square per gram is basically known as the mass absorption coefficient, and this is the most important variable that is considered for understanding absorption of various radiation. Now this mass absorption coefficient depends upon a constant k, lambda to the power cube, and z, which is basically the atomic number of the interacting material, to the power cube. Right. Now lambda is basically wavelength of the incident radiation. In this case it is X-rays. In case of neutron or electron it will be of neutrons and of electrons. K is a constant which is dependent on the type of radiation and is dependent on the interaction of that radiation. Say for example X-rays, it interacts with the matter in a different manner than that of the neutron and then that of the electron. So K constant will be dependent on that kind of electromagnetic radiation. So if we look into the X-rays as it interacts with shell electrons and nucleus too, it has a very high mass absorption coefficient for different materials, which is from which the information is being collected, right. So it is very high, that is about 30 centimeter square per gram to 400 centimeter square per gram. So in an average you can say that it's in a range of about 100 centimeter square per gram as given in most of the reference books and the textbooks. So you see, if we look into Valerie Randall and Olaf Angler book, where Introduction to Texture Analysis, the table for mass absorption coefficient for molybdenum, copper or cobalt, K alpha radiation when it is interacting with different matter is given. It is table number 3.4, so you can go and check it. So as if the intensity I0 is incidenting on a certain matter and then it is diffracted in a so let's say that it is in the reflection geometry or in the transmitted geometry, the incident the diffracted beam that is coming out, that is I, is given by equal to I0 exponential minus mu t, where t is the thickness of the the material through which the absorption has taken place. So the penetration depth of normal X-rays is in a range of 10 micrometer to 100 micrometer based upon this mu by rho, that is the mass absorption coefficient. If we look into the neutron diffraction method, the neutron basically interacts only with the nucleus, and you see that except when the material through which the interaction is taking place is magnetic, the neutron interaction in that case only become a magnetic scatter, which we are not considering in this lecture. So in those cases magnetic scatter occurs by the shell electrons, but you see in normal non-magnetic materials, polycrystalline materials, neutrons interact with nucleuses of the atoms, and you see as the size of the nucleus inside each of these atom, which is periodically arranged in a polycrystalline material, is very small as compared to the wavelength of the neutron. So the the atomic scattering factor of the neutron radiation is basically independent of the reflection, that is the diffraction angle theta, right. So you see not only the diffraction angle theta but all scattering angle theta, right. Even though you see the diffraction intensity will come larger because of the periodic structure following Bragg's law and structure factor calculation, but you see when you talk about the atomic scattering factor, it is independent of any theta scattering angle. When we compare and talk about X-rays and electrons atomic scattering factor, Fx and F electron, they strongly decreases with theta because it interacts with shell electrons and also with the nucleus in both the cases. So its interaction and atomic scattering factor decreases as theta increases. So, you see, in case of neutron diffraction, because there is a lot of empty space for the neutron to travel and the atomic scattering factor also do not reduce with respect to theta, its mass absorption coefficient, that is mu by rho, is extremely low as compared to that of the X-rays, and this is about, you see, 0.01 centimeters cube per gram. So, if it has such a low mass absorption coefficient, then it can go to a much higher penetration depth, and that is, it goes more than 10 centimeters. But you see that neutrons and X-rays, they, you know, the diffraction occurs from a large volume of grain, right? So, it has a large beam thickness, means beam diameter, and it diffracts simultaneously from many grains, right? And it cannot give a very small information from a very small area or a small, you know, diameter of beam cannot be produced. So, you see, if we look closely, neutrons, even though give information of penetration depth greater than 10 centimeter, but neutrons, you see, can only be produced in a nuclear reactor, and it should be only used if the information cannot be obtained from a normal X-ray diffraction or something. Okay, I forgot to mention here that the mass absorption coefficient mu by rho of the neutron radiation is also given in the same table, table 3.4 in Olaf Agler and Valerie Randall's book of Introduction to Texture Analysis, page of 65. So, you can check that, and you will be able to see that for various materials for which the neutrons will be interacting will have a different mass absorption coefficient, but that mass absorption coefficient is considerably lower than the mass absorption coefficient for the X-rays. So, what I was saying, that neutron radiations are usually produced in nuclear reactor, and I have seen one which is present in Germany in Helmholtz-Zentrum-Giesstadt in a small town of Giesstadt, and there the beam line for the neutron radiation is closed because of the environmental protection. So, I also support that. So, only when it is needed is usually used, but most of the beam lines which are there in most of the in the countries are basically closed, particularly in Germany. Electron diffraction method are used to obtain local texture, that we have come to a conclusion up to now, I think. But you see, if we look deeper, electrons interacts with both the shell electrons and the nucleus. It has a charge, and therefore it scatters the atoms, right? It's, you know, it has a very low lambda. So, you see, the theta, that is the Bragg's angles, will be very, very low. So, you see that if we talk about the atomic scattering factor of the electron beam, the atomic scattering factor of the electron beam are in 10 to the power 4 times, you know, higher than that of the atomic scattering factor of the X-ray beams and the neutron beams. So, high intensity electron scattering is there, therefore it can be used for high resolution in an electron microscopy, right? So, you see, because of this high intensity and very low wavelength, the mass absorption coefficient of the electrons are also very high. You see, much higher than that of X-rays and of course then for neutrons. So, it is about 10 to the power 4 centimeter square plus per gram. So, you see, then what happens, that the penetration depth will be much lower than even 1 micron. So, you see, depending upon the type of the material that it is interacting, the atomic number of the material. So, if you have a lower atomic number material like magnesium, then it will, in aluminum, then it will have lower penetration depth, and it will have, lesser mass absorption coefficient. If you have a material like zinc or other material which have a higher atomic number, so it will have a much lower penetration depth than even than the 1 micron. So electrons have charge. This charge is about 1.6 into 10 to the power minus 19. So it has low penetration depth and it has low interaction volumes. So electron charge can be used. You see what we can do, but in case of electron is that by utilizing a set of magnetic lens which are basically known as condenser lens, the electron beam can be converged or made parallel into very thin beam, such a thin beam that that beam can be utilized to produce very thin parallel beams to obtain information from the smallest pixel possible, right. So one can obtain high resolution image in a ACM or a TEM rather, right. So TEM is mostly used for most higher resolution images than the ACM basically, because ACM is in reflection geometry and then its resolution decreases because many geometric factor, whereas the TEM we have the direct beam where the resolution can be kept to a much higher level. So you see that in case of TEM, the spatial resolution of the electrons can be obtained up to say 1 nanometer, which is extremely high, and the angular deviation is less than 0.1 degrees. Whereas in case of you see ACM and EBSD particularly, where we are getting quantitative microscopy, the spatial resolution is less than 0.1 micrometer and accuracy level of 0.5 degrees. Now you see that with the advent of technologies and near developments, this spatial resolution of the ACM is constantly decreasing, and now we have seen that we are able to obtain even grains of the size of 150 250 nanometers in a polycrystalline nanostructured grains in case of using an ACM EBSD. So this higher spatial resolution allows you see diffraction from not only individual grains only, but even from a very smaller parts of the individual grains of submicron structured individual grains, and therefore we can obtain micro texture. So here we conclude that, and then we come to X-rays. So the question is, how were X-rays generated basically? So initially when the X-rays were developed, it was developed by Röntgen in 1895, and during that time continuous X-ray was developed. And what is continuous X-rays? Continuous X-rays means the X-rays which are polychromatic in nature and they have different wavelengths, right. So that kind of X-ray was developed. So if you see that how an X-ray is developed, there is a tube, and in the tube there are two metal electrodes. One if you say is cathode, another if you say is anode, right. And this two electrodes inside a tube is kept at a very high vacuum, and when a voltage is applied between this anode and the cathode, which are separated from each other, say it is increased from 1 kilovolt to 3-4 kilovolts to 10 kilovolts, something like that, and the voltage is constantly increasing, then what happens that the electron starts to generate and starts to travel towards the anode. So electrons generated at cathode travels towards the positive anode because of the electronic charge difference created by the voltage, right. So the electron starts moving towards the anode at a very high velocity, so it hits the anode at a very high velocity. So you see when the electrons hits the anode, what happens, there is a rapid deceleration of the electrons hitting the anode, and because of this rapid deceleration of the electrons hitting the target anode inside the tube, it radiates certain kind of energies of certain wavelengths which are known as X-rays. This radiation of X-rays occurs in all possible direction, right. So you see, if we talk about this, mathematically, and we say that okay, the kinetic energy of the electron is equal to E into V, where E is the electronic charge and V is the voltage that we are giving to the material, and then the that becomes equal to half mv square, where m is the mass of the electron and v is the velocity that it can travel, right? So if we know the electronic charge is basically 1.6 into 10 to the power minus 19 coulomb, and m, the mass of the electron, is 9.11 into 10 to the power minus 31 kilograms. So if we give a tube voltage of 30 kilovolts, you see, so using this equation we can find out the velocity of the electron is equal to root of 2 electron uh, in coulombs into voltage, that is 30 kilovolts. This is the one, divided by the the mass. So 9.11 into 10 to the power minus 31. So it comes out to be 1 into 10 to the power 8 meter per second is equal to 1/3 of the speed of the light. It is very high. So you see that kind of energy from an electron is going into the target, and when it is decelerating, it is producing some kind of energy in form of electromagnetic radiation of various wavelengths because of the deceleration, and this is known as continuous X-rays. So you see, as the voltage is increased, what happens that the number of photons per second that is hitting the anode increases, and the average energy per photon also increases. So what happens is that the X-ray intensity of the continuous spectrum then becomes equal to A, which is a proportionality constant, I, the current inside the X-ray tube, Z, that is the atomic number, V, that is the voltage, and M, which is also a constant, which is usually in and around 2 for most of the cases, gives the intensity of the continuous X-ray spectrum. So before we go ahead, we should know that most of the kinetic energy of the electrons that are hitting into this anode target is mostly converted into heat, and only 1% is actually converted into this continuous spectrum X-ray radiation. So this is also very important to understand that very few only 1% of the energy is converted into X-rays. So if we look into this diagram of X-rays, it is a diagram which is it's a schematic one, and it's also given in most of the books in some way or in a different manner. So you see, it shows the x-axis as the wavelength in Armstrong, and you see the y-axis as the X-ray intensity in some arbitrary unit. Okay, so you see that when the continuous radiation, that is a polychromatic radiation, it is also known as white radiation, it is also known as Brahmastra long, it is also known as heterochromatic radiation or continuous radiation. And you see that this continuous radiation looks something like this. If you look into my pointer for, you see, 5 volt, and when these are all actually 5 kilovolt, 10 kilovolt, 15 kilovolt, 20 kilovolt and 25 kilovolts. Volts is wrong, so I have to correct it. So you see, when the voltage is increased from 5 kilovolt to 10 kilovolt, what happens that the lambda start, or the minimum lambda, or the usually it is known as the lambda short wavelength lambda, basically decreases. You see, when it goes from 5 kilovolt to 10 kilovolt, the short wavelength lambda decreases, and then it goes to 15 kilovolt, it decreases again, and 20 it decreases again, and 25 it decreases much more. So lambda SWL, that is the short wavelength lambda, keeps on decreasing as the voltage keeps on increasing. So you can see, you can realize that not only lambda, but also if you look, the maximum of the the maximum of this peak, the peak maximum, that is the lambda maximum, also you see decreases as the voltage of the X-ray tube is increased. So you see, as the voltage increases from 5 kilovolt to 10 to 15 to 25, what happens is that the energy by which the electrons are hitting the target anode increases, and therefore what is happening that as the energy is increasing, the lambda is basically inversely proportional to the energy of the applied radiation. So the lambda, because the frequency is increasing and frequency and lambdas are inversely proportional, so the lambda is basically decreasing. That means high energetic X-ray beams are being produced with the increase in the voltage of the X-ray tube. So you see that not only lambda WSL, but you see the lambda maximum also decreases towards the lower lambda value. So you see, so there is a short wavelength limit gamma WSL. Intensity is 0 below that short wavelength limit for any kilovolt applied to the X-ray tube, but you see there is no specific limit for the long wavelength side. You can see that in the long wavelength side, where the energy is keeping on decreasing, that is on the right side, there is no specific stop. So we have seen that as the voltage increases, the intensity increases, and thereby the lambda WSL and the lambda maximum actually decreases, and this is given by these equations, right? So energy is equal to electron volt is equal to h mu. H is the Planck constant, mu is the frequency. So h, this equals to h c by lambda. C is the speed of light, and you see that energy is inversely proportional to lambda. So the lambda basically decreases. Both lambda SWL and lambda maximum basically decreases. So see, what is lambda SWL? Whenever the electron is striking and it is decelerating inside that target anode, it is producing this continuous spectrum, right? But if you see that the maximum energy can be produced if the deceleration is maximum, right? And when the deceleration is maximum, only when the electron is stopped at only one impact. So it can give the maximum energy, right, at once. So when it produces a photon of the maximum energy, then the X-ray with the minimum wavelength or the soft wavelength limit is produced. So one can use this same equation to calculate the short wavelength limit for different voltages, and you can see that we have given that the energy is equal to electron volt. So electron charge into volt of the X-ray tube equal to h into mu max. Therefore this means that the frequency will be maximum, and therefore h c by lambda will be minimum. So the lambda SWL, that is the short wavelength limit, is basically given by h, which is the Planck's constant, c, which is the velocity of the light, divided by the charge of the electron and divided by the voltage of the X-ray tube. That means the voltage at which the electrons from the cathode is hitting that target anode. So if we calculate the lambda SWL, it becomes equal to 1.24 into 10 to the power 4 per unit voltage. That means one can calculate the lambda short wavelength limit for different voltage, 5, 10, 15, 20 or 25 kilovolts, right? Now you see that when the voltage is increased, so when it is increased to 25 kilovolt from 20 kilovolts, for example in this case, so what happens that suddenly there are some peaks that forms in this kind of continuous radiation curve, and these peaks are basically, for example in this case it is shown to be k alpha peak, k beta peak, and they have a specific lambda. You see that this specific lambda even do not change if the voltage is further increased to 30 kilovolt, 35 kilovolt or even 100 kilovolt. Only the intensities of the K alpha and K beta radiation will increase many a times as compared to the intensity increase of this continuous radiation. So, this radiations having particular values of wavelength and with a very thin integral width are basically known as characteristic radiations. That means a radiation having certain specific wavelength and therefore can be utilized for doing diffraction measurements, and we are basically looking into these characteristic X-ray radiations. So, if we magnify that part of that curve and show in terms of, you see, X, here is also wavelength in Armstrong, and Y, that is X-ray intensity in arbitrary units, and you can see that the K alpha may look like this and the K beta may look like this. So, K alpha forms at a little higher lambda than the K beta, and K alpha has a much higher intensity as compared to the K beta. The integral width of K alpha K beta is actually very small, and therefore it belongs to a certain specific wavelength. Now, if we magnify further, we can see that K alpha is not a single K alpha, does not have a single intensity, but it may have two different intensities, K alpha 1 and K alpha 2, very closely but separated. So, you see, as I said in the previous section, previous slide, that as the voltage is kept on increasing, the sharpness of this K alpha, K beta and the K alpha 1, K alpha 2 etc. keeps on increasing, but these particular wavelength remains the same. So, this is basically the characteristics of that particular anode target in which the electron beams from the cathode is hitting, right. So, that means some radiations which are coming from the K shell, or because of the electronic movement from some shell to some other shell is happening, this kind of radiation is taking place. So, you see, there could be characteristic lines from the K shell, from the L shell, M shell, and therefore each will have different lambdas, and it is well known that the radiation from the K shell will have a lower lambda, that means a higher energy, higher frequency. From L shell and M shell it will be of a little higher lambda, and therefore it will have a lower energy. Let us go deeper into it. You see that the K shell, as I said, can be divided into K alpha 1, K alpha 2, K beta 1, and it is shown in this schematic picture. And you see that K alpha 1 and K alpha 2 are extremely close together. If it can be resolved, then it is called the K alpha doublet, and you can see this doublet, and if it cannot be resolved, then it is called the K alpha line, and the K beta 1 is basically the K beta. So, the maximum voltage that requires to excite these characteristic K radiation is basically known as the critical K excitation voltage, and this is very important to understand. Below this K excitation voltage, this characteristic lines could not be observed, right. So, you see, if we increase the voltage above this critical voltage, the intensities of this K alpha K beta will increase, but it will increase with respect to the continuous radiation, but the lambda remains the same, and that's we already talked about in the previous slides. So, you see that how this characteristic X-rays can be generated. So, before we say that, W.H. Bragg basically discovered this characteristic X-rays, right, and then you see when the voltage is increased and the velocity or the kinetic energy of the electrons inside that X-ray tube increases and it hits the target anode, and that if that electron's energy is sufficient enough, if it is sufficient enough, if the kinetic energy of the electron is enough to knock down a particular electron from a certain shell, say if it knocks down an electron from the K shell, if it knocks down, if this is an atom, this is a nucleus and these are the electronic shell, that is the K shell, L shell, M shell, and if the electron comes and it can have the enough kinetic energy to knock down an electron from the K shell, then the atom goes to a higher excitation state, that is a higher energy state. And when it goes to the higher energy state, in order for the atom to come to the normal state, an electron from the outer electron shell, say for example from the L shell or from the M shell, basically falls on the K shell vacancy to to dissolve this vacancy, and in this process emits an energy of a certain wavelength to, and the atom comes to the normal energy state again, and this certain wavelength energy, that is a characteristic wavelength energy, is basically the K alpha K beta radiation. So K alpha radiation is basically when the electron from the L shell falls on the K shell, and K beta radiation is when the electron falls from the M shell to the K shell, right. So now you see that the probability of filling the probability of filling the K shell from the L is actually much higher than that of the probability of filling the K shell from the M shell. Therefore, you see all the time, in all cases, all the different anode metals, the K alpha is much stronger than the K beta radiation. So you see, similarly, when the K excitation energy of the electron becomes higher and it is sufficient to generate radiation X-rays characteristics of certain K alpha or the K beta ones, then this energy is even sufficient to excite electrons from the, means to knock down electrons from the L shell and the M shell too, producing L alpha and M alpha radiation, right. In a similar process, these L alpha, M alpha radiations can be generated even at a lower K excitation voltage, right. So this characteristic L alpha and M alpha radiations will have a higher wavelength and a lower energy, and therefore the K alpha and K beta radiation cannot be obtained without the formation of L alpha and M alpha radiations. So you see that Sigborn et al. Actually gives the measures the wavelength of all the characteristics X-rays for all the elements, and they have documented it, and this can be obtained from the Sigborn et al. If you look into the internet. So you see that while we are talking about this characteristic radiation, one should remember the Moseley's law given by H.J. Moseley, and that is that root of frequency is equal to C, which is basically constant, times Z, which is atomic number minus of sigma. So root of mu is a frequency, C and sigma are constants, Z is atomic number, and so the Z is equal to root of 1 by lambda, right, because mu is equal to 1 by lambda. So you see that as the Z increases, the characteristic wavelength lambda basically decreases. So higher the atomic number of the target anode, the characteristic K alpha radiations lambda basically decreases. This is a good thing to remember, good thing to know, because as the lambda is decreasing, one can get information of diffraction from elements whose periodic arrangement of atoms are closer, right, are more closer, and therefore one can get information which cannot be obtained from certain X-rays where the lambda is higher than the periodic arrangement of those atoms. So, what we can conclude here? We can conclude that X-rays have high mass absorption coefficient, about you see 100 centimeter square plus per gram, and therefore has a lower penetration depth of 10 micron. There also it is suitable to measure macro texture. Synchrotron X-rays have lower wavelength than the normal X-rays, and because they have lower wavelengths, they can have a lower mass absorption coefficient, and therefore its penetration depth is increased to millimeter level. Neutron diffraction on the other hand have very low mass absorption coefficient and therefore very high penetration depth to centimeter level. Electrons have very high mass absorption coefficient, about 10 to the power 4 centimeter square per gram, which is much higher than that of the X-ray, and therefore its penetration depth is not even 1 micrometer. So, the characteristic X-rays are generated by electrons of sufficient kinetic energy that must be sufficient to knock down a k-shell electron, so that the atom can go into a excited or a higher energy state, and then the outer shell electrons from the L or the M shells falls on the k shell to fill up that vacancy in the k shell, generating a energy of a specific wavelength, that is lambda. So, that is all for today's class. Thank you.